Here we're going to go through 3 examples where we start with a Boolean equation and find the truth table and also find the optimized digital circuit. So the first example we're going to look at is f equals jk ANDed with I ORed with k prime. So the first thing we can do here is we can say f is equal to jk distributed to the quantity I ORed with k prime. So we will write jki ORed with jk k prime. Now, when k is ANDed with k prime as shown here, we can say that k and k prime equals 0. Now, why is this the case? If k is 0, k prime is 1, and those two together, 0 ANDed with 1 is 0. K equals 1, so k prime equals 0, and these two together, 1 ANDed with 0 is always 0, so we know that k and k prime is equal to 0. This drops. 0 ORed with anything is equal to, or 0 ORed with a variable is equal to that variable. So we can say that this is I, j, k ORed with zeros, so we can drop that. So we have our final equation, f equals I, j, k. Let's try and write the truth table. How many variables do we have? 3 variables. So we have 2 to the power of 3 input combinations, combos. So let's list our variables and our output variable. I, j, k, output variable f, we'll list all possibilities here. 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And then k is just alternating zeros and ones. And we have all 8 possible input combinations. So 2 to the power of 3 is 8 input combinations. So when I is equal to 1 and j is equal to 1 and k is equal to 1, then f is equal to 1. Since there are no other possible input combinations where f is equal to 1, we cannot list any more entries for 1, and we just list the rest of them as 0. Output 0. So our final output, or our final digital circuit, is simply a 3-input AND gate. Output F, I, j, and k, like so. So now we have the truth table and an optimized digital circuit, like so. Our next example is more complicated. G equals A and B and C prime, ORed with B and C prime and D prime, ORed with C and D, ORed with A prime and B. So to simplify this is a little bit trickier. We're going to have to make it more complicated to make it simpler. So the first thing we're going to do is we're going to notice that we have an A prime B here, and we're going to try and combine it with this term here. So how do we do that? Well, let's reorder first. Equals A, B, C prime, or A prime B, or B, C prime, D prime, ORed with C, D. Okay. Now, we can notice that A prime and B can be extended. So we get A prime and B ANDed with 1, and we can notice that 1 is also equal to C ORed with C prime. C or C prime equals 1. We need to use this identity. Remember, if C is 0, then C prime is 1. 1 ORed, 0 ORed with 1 is 1. If C is 1, C prime is 0, and 1 ORed with 0 is 1 again. So C or C prime is the same as ANDing with 1. So let's distribute A prime B to this quantity C or C prime. Equals A, B, C prime, or A prime, B, C prime, or A prime, B, C, or B, C prime, D prime, or C, D. This quantity here, or this term here, A prime, B, C prime, can be combined with either this term or this term, but not both. But we can get around this problem by using idempotency. So remember that K ORed with K is equal to K. 0 or 0 is equal to 0, and 1 ORed with 1 is equal to 1. So idempotency holds, so we can duplicate A prime, B, C prime. Let's do that. A, B, C prime, or A prime, B, C prime, or A prime, B, C prime, or A prime, B, C. Now that we've listed the 4 terms from the first 3 terms of the previous line, we're going to just copy these 2 terms now. B, C prime, D prime, ORed with C, D. Now, we can factor out A, B, C prime from these 2 terms, and we can factor out an A prime B from these 2 terms. So let's do that. Equals B, C prime ANDed with A or A prime, and we OR this with A prime B. We AND that with C prime or C. Notice that we're using this theorem here again. So A or A prime becomes 1. C prime or C becomes 1 as well. And we can also copy these 2 terms again. B, C prime, D prime, or C, D. So let's take a look here. We now have a more simplified equation, B, C prime, or A prime, B, or B, C prime, D prime, or C, D. Let's give ourselves some more space here. Now, if we look closely, we have a BC prime term here and a BC prime term here. We could factor that out using the distributive property again. So BC prime ANDed with 1, because if we factor BC prime from itself, we get a 1. And then we OR that with D prime because we took it out from this term here. OR that with A prime B or C, D. Now, 1 ORed with anything is always equal to 1, so we can get our final simplified formula equals B C prime or A prime B or C D. Like so. So now we can use this equation to develop our truth table. How many input variables do we have? We have 4. So 4 input variables. This gives 2 to the power of 4 equals 16 input combinations. Let's draw this table out. So what are our variables? A, B, C, D, and our output variable, G. Okay. So 0, 0, 0, 0, 0, 0, 0, 0. So half of the entries have A equal to 0. Half of the entries have A equal to 1. 1, 1, 1, 1, 1, 1, 1, 1. Let's format our tables so that it's a little easier to read the separation of the rows. We can draw lines here for every 4 entries. Now B should have 8 zeros and 8 ones. We will go by 4s. 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. By 2s for C. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And finally, alternating every entry for D. 0, 1, 0, 1, 0, 1, 0, 1, etc. So now, let's go through our 3 terms here. Let's look at this term first. We know that G is going to be equal to 1 if and only if one of these 3 terms, BC prime is true, or A prime B is true, or CD is true. So what entries are, in which entries is the term BC prime true? So B is equal to 1 and C is equal to 0 for this term to be true. So BC prime, so when this column is 1 and this column is 0, we're going to have 1s for G. So 1, 0, 1, 0, and then 1, 0, 1, 0. Let's look at A prime B. So when A is equal to 0, so A prime is equal to 1 then, and B is equal to 1, so A equals 0 and B equals 1. What are the entries that for this condition? So this entry must be true here. This entry here, these are already listed, but also these 2 entries as well. 0, 1, 1, 0 and 0, 1, 1, 1. So we will list those as having an output of 1. Finally, we come to entry CD, when C is 1 and D is 1. So there are 4 entries here in the table. C is 1 and D is 1 here. C and D are both 1 here. C and D are both 1 here. And C and D are both 1 here. And now that we have covered all the terms, all the remaining entries are 0. And this gives us our truth table. Now, keep in mind that if you used the original equation, which we started with, up here, then you would get exactly the same truth table. G is equal to G, so if you simplify, you should get the same truth table, regardless of what modifications you made. If you get a different output, then there was an error in your optimization strategy. Now let's look at writing an optimal digital circuit based on this equation here. So we have an invert. We have A, B, C, and D. So we have A, B, C, and D. Let's draw the variables. And label them. These are our inputs. We then need A prime and C prime, so we need 2 inverters. A prime and C prime, and then we can list our outputs here for these 2 inverters, prime and C prime. And now we need 3 AND gates for B, C prime, for B, C prime, and A prime and B, and C and D. Oops, our label is incorrect. This should be D, not B. Now that we have these 3 AND gates, we can OR them together. We can use a 3-input OR, like so. And then we have an output G. This gives us our digital circuit. So our last example of a Boolean equation where we convert to a truth table and a digital circuit is H equals A ANDed with the quantity B prime and C prime, or B and C. Now, one thing we can look at here is that it's possible to distribute the A to the B prime, C prime, and the BC terms and simplify somewhat. So here, if we count the gates, we have an OR gate, that's 1. We have an AND gate, 2 inverters, and another AND gate here. So that's 1, 2, 3, 4, 5, 6 gates. If we distribute, we get A, B prime, C prime, or A, B, C. This gives us 1 gate, 2 gates, 3 gates, 4, 5. So that's 5 gates if we'd use the distributive property. However, one detail that we should notice is that B prime, C prime, ORed with BC. Let's call this K as a temporary variable. We can look at this in a truth table and notice an interesting optimization. So we'll say BC and we'll write the truth table for this 2-input variable k. 0, 0, 0, 1, 1, 0, and 1, 1. When b and c are both 0, k is equal to 1 by this term. When b and c are both 1, k is equal to 1 by the bc term. For all other terms, k is equal to 0. This truth table represents an equivalence gate. So we have b k equal to b XOR c prime, which is also the same as b equivalent c. So our h value we can reduce even further and say h equals a ANDed with b equivalents c. And we have our most optimal circuit in terms of the minimal number of logic gates. How do we draw the digital circuit? We can first draw the equivalence gate like so, or the XNOR. We have B XNOR C. And then we have an AND gate. This takes an input A and an input from the XNOR. And finally, we get our output H. So while it is possible to reduce this to 5 gates, the optimal case here uses the equivalence gate. So let's develop a truth table for this Boolean algebra equation here. We have 3 input variables. And so we have 2 to the power of 3 equals 8 input combinations. So let's list these out. A, B, and C, and our output variable H. So all possible input combinations: 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, oh, I'm sorry, 0, 0, 1, 1 will go by 2's for B, 0, 0, 1, 1, and then by 1 for C, 0, 1, 0, 1, etc. So what are our possible values of 8? What possible entries for H give us a value of 1? Well, the first thing we see is that A must be equal to 1. So only these 4 combinations are possible. Also, B must be the same value as C. So we have values here and here. All other entries are 0, therefore. This concludes our discussion of some examples of how to convert Boolean equations into truth tables and optimal digital logic circuits.